Hey everyone, we're diving into some breaking news today with the latest updates from the National Transportation Safety Board, NTSB, and the Federal Aviation Administration, FAA, about the tragic crash of UPS Flight 2967, an MD-11 cargo jet. This devastating incident happened when the plane departed from Louisville, Kentucky, headed for Honolulu, and ended in catastrophe. In this video, we'll break down what's known so far about the engine detachment that led to the crash, and we'll draw comparisons to a hauntingly similar disaster from decades ago, American Airlines Flight 191 in 1979. We'll also unpack the maintenance scandals tied to that earlier tragedy and how they reshaped aircraft design. Now, we're not saying the same exact issues caused the UPS crash, but there are striking parallels worth exploring. Stick with us as we dig into the technical details of these McDonnell Douglas trijets, from their unique three-engine setups to the pylon mounting systems and the intense aerodynamic forces at play during takeoff. We'll also look at potential failure points like fatigue cracking or torque mismatches that could lead to disasters like this. If you find this deep dive fascinating, drop a 1 in the comments to let us know you're digging the content. Let's start with the UPS Flight 2976 crash. According to the NTSB's preliminary findings, the left-wing engine, known as the number 1 engine, a powerful General Electric CF6-80C2 high-bypass turbofan pumping out over 60,000 pounds of thrust, completely detached during the takeoff roll. It separated right at the pylon wing interface, a critical connection point. Eyewitness accounts, video footage, and flight data paint a grim picture. The aircraft pitched sharply to the left as the sudden loss of thrust and asymmetric drag from the missing engine and nacelle threw it off balance. The plane stalled, slammed into the ground just past the runway's end, and erupted into a massive fireball. It barely cleared the airport fence before crashing into nearby terrain and buildings. The FAA's on-site team reported that parts of Louisville's airport remained closed, with taxiways cordoned off as investigators combed through wreckage scattered over nearly half a mile. This MD-11 freighter, registered as N259UP, was a stretched version of the DC-10, boasting a 206-foot wingspan and a maximum takeoff weight of over 650,000 pounds. It was fully loaded for a trans-Pacific journey, with cargo secured on its reinforced main decks. The takeoff occurred around 5:15 p.m. local time under clear skies, with no significant weather issues reported at the time of the incident. So why did that engine break away? The NTSB and FAA are urging patience as they investigate, with no official cause determined yet. But some potential culprits are already being discussed. It could be pylon failure due to high cycle fatigue in the aluminum alloy fittings. Think tiny micro cracks forming from the repeated stress of pressurization cycles during flights, eventually growing under the heavy loads of takeoff. Other possibilities include mounting hardware problems like loose or corroded shear pins, or even resonance-induced vibrations causing stress fatigue during the high-power spool-ups these engines endure on every flight. UPS is fully cooperating, providing maintenance logs for the aircraft, including recent tests on the pylon, engine, and other critical components. But for now, it's all speculation until the final report comes out. Just a heads up, we're not official investigators here, just breaking down the info as a pilot and aviation enthusiast sharing insights on YouTube. Now let's turn back the clock to May 25, 1979 for a chilling comparison with American Airlines Flight 191. This DC-10, bound for Los Angeles from Chicago's O'Hare International Airport, carried 271 souls on board. Powered by 3 General Electric CF6-6 engines, each delivering 40,000 pounds of thrust, this wide-body trijet lifted off only to face disaster 31 seconds later. The left engine and its pylon tore free, cartwheeling over the wing at a climb rate of over 300 feet per minute. The aircraft banked hard left, spiraled toward the ground, and crashed, killing everyone on board plus 2 people on the ground. It remains one of the deadliest single aircraft crashes in U.S. history. Unlike the UPS incident, where debris from the detached engine may have caused a compressor stall in the tail-mounted number 2 engine, the American Airlines crash didn't show that specific issue. But the root cause, as the NTSB later found, was tied to shocking maintenance shortcuts driven by cost-cutting in the post-oil crisis era. American Airlines ditched the factory-recommended engine removal process, which used a crane to handle the engine alone and avoid stressing the pylons. Instead, they opted for a faster, cheaper method using a forklift to remove the entire engine pylon assembly, slashing maintenance time from 68 to 26 man-hours. This reckless shortcut had deadly consequences. 2 months before the crash, during a reinstallation, a forklift slipped and damaged the pylon by slamming into the wing's underbelly at the forward bulkhead. This caused a half-inch misalignment and cracks in the left clevis pinholes, but inspections missed them because the rushed process skipped critical torque checks on the pylon's fittings. These fittings included 1-inch diameter pins designed to handle 100,000-pound shear loads, absolutely vital to keeping the engine secured. That single oversight snowballed into tragedy. Repeated flights with an improperly seated engine created stress fractures throughout the assembly, exacerbated by G-forces as high as 2 during normal operations. Congressional hearings later slammed American Airlines for prioritizing efficiency over safety, relying on visual inspections instead of advanced testing for hidden flaws in the metal. McDonnell Douglas also faced heat for unclear manuals that enabled such risky methods, and the FAA admitted to certification lapses by not fully testing the forklift procedure under full engine load. In the aftermath, inspections of other DC-10s revealed 9 more aircraft with similar pylon cracks, often undetected until invasive dye-penetrant tests exposed them. The FAA grounded all 273 U.S.-registered DC-10s for weeks, mandating X-ray inspections of pylon fittings and redesigning them with stronger aluminum rated for 150% overload. McDonnell Douglas returned to separate engine and pylon removals, using specialized rigs for precise alignment within 0.01 inches, added redundant shear pins in double-row configurations, and improved load distribution with spherical bearings that cut bending moments by 40%. They also tackled a critical issue from the crash. When the engine detached, it severed hydraulic lines at 3,000 psi, retracting the left wing's leading-edge slats and causing asymmetric lift with a 15-degree roll rate. To prevent this, they introduced backup hydraulic circuits with electric pumps and slat blocks using solenoid-actuated pins to keep slats extended up to 250 knots even if an engine broke free. Fast forward to 1990, when the MD-11, successor to the DC-10, and the aircraft type in the UPS crash, was introduced. It incorporated these hard-learned lessons with a refined airframe, a 192-foot stretched fuselage for better stability, and retained the tri-jet layout with CF6 or PW4000 engines delivering up to 93,000 pounds of thrust. Its pylon structures used enhanced forged titanium fittings resistant to fatigue, with crack-arresting doublers and vibration isolators tuned to dampen frequencies above 50 Hz during takeoff. If you've ever been on an airliner during takeoff, you know how everything shakes. That's why securing every component is crucial. The MD-11 also features 3 independent 3,000 psi hydraulic systems. any one of which can handle full flight control, plus electromechanical slat backups with position sensors feeding fly-by-wire systems for automatic asymmetry compensation. Engine mounts include elastomeric dampers to absorb gyroscopic torques. And freighter variants like UPS's have reinforced floors with 1.5G cargo tie-downs to minimize flex from pylon stress. These upgrades have given MD-11s over 10 million flight hours, with a dispatch reliability above 99%. Yet, the UPS crash suggests vulnerabilities might linger if pylon integrity or inspections falter, especially on airframes with over 75,000 cycles of takeoffs and landings. So, what ties these two crashes together and what sets them apart? Both involve McDonnell Douglas trijets losing a left engine during takeoff, a rare and catastrophic failure. In each case, the loss of thrust and asymmetric drag triggered a violent left yaw, leading to a stall and loss of control. For American Airlines 191, the pylon failure severed hydraulic controls, dropping pressure to zero and retracting slats. Early UPS data shows a similar role in stall, with bystander footage capturing the left wing dipping, possibly worsened by the tail engine ingesting pylon debris, a factor not reported in 1979. Both crashes likely occurred past V1 decision speed, around 150 knots for the DC-10 and 160 knots for the MD-11, meaning the pilots were committed to takeoff, with no way to abort. Undoubtedly, the crews in both incidents fought to the end, battling uncontrollable yaw and roll. Key differences include aircraft design. The DC-10 had a simpler dual hydraulic system, while the MD-11's triple redundancy offers more backup. Maintenance was a clear factor in 1979 due to inadequate inspections and a culture of cutting corners, but with UPS, it's too early to say. Metal fatigue could be a shared issue, especially if the MD-11's high cycle count demanded more frequent or advanced thermal and X-ray inspections. The NTSB's full investigation into UPS Flight 2976 will take 12 to 18 months, focusing on pylon fractures and metal fatigue through electron microscopy to spot irregular cracking from overloads or overuse. Expect updated maintenance and inspection requirements to emerge. If lapses like inadequate torque checks or missed ultrasonic scans are found, the fallout could be massive for involved parties, though nothing points to that yet. Parallels to American Airlines 191 might trigger fleet-wide MD-1 inspections, and if cracks or procedural flaws surface, we could see retrofitted kits or even new pylons using advanced materials like carbon fiber reinforced composites. UPS, with a strong safety record, 0 prior detachment events, and 1.2 million MD-1 flight hours, uses cutting-edge tools like AI-monitored logs and drone-based thermography for hotspot detection, far tighter than 1979 standards. This might prevent a full MD-1 ground stop, though recommendations could include enhanced pylon scans, material upgrades to 750 series aluminum for 20% better crack resistance, or software updates for early vibration detection in engine control units. These steps could finally close the book on trijet detachment risks. Thanks for sticking with us through this detailed breakdown. The NTSB will release more findings over the coming months and year, and will keep you updated as news develops. Our thoughts and prayers go out to the crew, the UPS family, and everyone affected on the ground by this tragedy. If this video resonated with you, drop a 1 in the comments to show your support. We'd love to hear from you. See you in the next video.